Okay, hello everyone and welcome to heat transfer. This is the problem we're going to be doing. If you want to just kind of draw out what you think you're going to be doing with this, go ahead and pause the video here. I'm just going to move right on into the solution here pretty quick. So what we're looking at right now is a silicon chip, first of all, that's just sitting by itself inside an airstream that's moving at 20 meters per second and has a temperature of 24 degrees C. But then as a second part, we need to figure out how much heat is transferred when you have an unheated strip of a substrate that the silicon chip is attached to, so that air flows over the substrate first and then onto the silicon chip. So we have to figure out those two separate conditions. Right here from table A4 for air, T film is equal to 325. If you're not familiar with T film, it's basically a median temperature between T infinity and T surface. So the T film in this case excuse me, the T of the surface is 80 degrees C. So T film is equal to 80 degrees plus 24 degrees, 24 degrees C all over 2, which is just the average of those two, the T surface and the T infinity. We're using 80 degrees because that's the maximum temperature that this chip can be at. And if you do this calculation and then turn it into Kelvin, you'll get this value down here of 325 Kelvin at 1 atmosphere. And then if you do the conversion on the air and the viscosity, and you'll get all these other properties out here. Okay, so now I'm just going to jump right into this analysis. Pause the video a second ago and get that drawing because I'm probably not going to show it again. So the first thing you have to do when you show one of these problems of air flowing over something, you need to figure out whether it's laminar flow or turbulent flow. So you need to figure out the Reynolds number. Reynolds number for the length of the piece that you're working with. So you've got the velocity of infinity, you've got the length of the total piece of plate or substrate and chip or whatever, and then you've got mu, which is the viscosity. And if you do this calculation for just the silicon chip, which is the 10 meters long, just the chip sitting by itself, then you've got 20 meters per second times 0.01 meters, because the chip is 10 millimeters long. All of the viscosity, which is 18.41 times 10 to the negative 6 meters squared per second. And this will give you a Reynolds number of 10,864. Now, in this problem, we're assuming that the critical Reynolds number, is equal to 5 times 10 to the 5th. So since this Reynolds number is less than the critical Reynolds number, this one's laminar. And then if you find the Reynolds number for the chip and the substrate together, which is 0.3 meters, you have the 20 meters per second, so on and so forth. Oh, sorry. In air. You've got 20 times 0.03 meters for this calculation, and then the same viscosity underneath, and you end up with that equaling 32,591, which is still less than the critical Reynolds number. So this case is laminar too. So we know that in both of the situations, with the chip by itself and with the substrate attached, the flow is laminar. So now what we need to figure out is finding the maximum Qmax, that can be transferred from the plate. So in order to do that, I'm actually going to figure out what the heat flux is, because that's going to be a little bit easier to do as a general equation here. So if you look at this as heat flux, Q double dot of the length, it's going to be equal to H, the heat transfer coefficient, times Ts minus T infinity, which means that Qmax, the heat transfer rate, this is the heat flux, will equal A of the surface, the area of the surface, times Q double prime. So that's just going to be a little intermediary step here. So we're going to go ahead and try to find HL for this situation, because we have the T of the surface and we have the T of the air. So now, you're going to need to use, and whenever you have to try to find H or H bar in a situation, you always have to use Milliset number. So, what we're going to do is have the Milliset number is equal to HL over K of the fluid, the air, not to be confused with bio number. And then you move on, and this is also equal to In this problem, it's going to be 0.453 times Reynolds to the 1/2 times the Prandtl number to the 1/3. So we're looking for H here. So if you rearrange this a little bit, you'll end up with HL equal to K over L times 0.453 Reynolds to the 1/2 Prandtl to the 1/3. And this is just by using the two definitions for Nelson number. Excuse me. And we're doing this calculation without an unheated starting length. You can basically, we just have the chip sitting here, which is 0.1 meters, 0.01 meters long. And that's how you are able to use this particular equation for the Nelson number. This is for just airflow, laminar airflow over a plate, is this equation for Nelson number. Okay, if you do this calculation, you'll end up with K. We were given the values of K up at the top. I established those already. K is equal to 0.0282 watts per meter Kelvin. Oops, sorry, I left my camera. Watts per meter Kelvin. And then length, as I said, is 0.01 meters. Okay, and if you figure that out, then you get HL is equal to 118 watts per meter squared Kelvin. So that's your H bar. You plug this back in the heat flux, and you get Q double dot of L over the length is equal to 118, which we just found. I'm not going to put the units in here because it's pretty easy. And then 80 degrees minus 24 degrees C. And if you solve that out, you'll end up with 6,630 watts per meter squared. And that'll give you a Q maximum equal to 10 to the negative 2. Actually, sorry. Qmax is the area, 0.01 squared, because it's a square chip, 0.01 meters on either side, times Q double dot, which is 6,630 watts per meter squared, and you'll end up with 0.66 watts. So this is the maximum amount of power that chip can transfer or take without overheating. So now we have to do the same calculation for the chip with a substrate attached. So we've got the chip right here, and then we've got a substrate over here, so we've got 0.02 meters and 0.01 meters, if you don't have that drawing from before. So now, in doing this part, the Nelson number equation changes. So we've got NU is still equal to HL over KF, but now it's also equal to, keep on breaking my lead, sorry, the Reynolds number to the 0.453 Reynolds to the 1/2, Prandtl to the 1/3, all over. This is where this difference. When you have a unheated starting length, you put in this denominator. Otherwise, this denominator basically goes to 0 when you don't have a starting length, and you'll see why in a second. 1 minus zeta over L, and this is the total length, 0.02 plus 0.01, to the 3/4 to the 1/3. Now, note about these two coefficients. These are based upon if you're using UST or UTD systems within these, and those are defined usually by the problem or by the professor, hopefully, if they're trying to help you out at all. But these two exponents are normally listed as A or B in the equation, and you figure out if it's 3/4 or 1/3 based on a table. Let me see if I can find that table here for you, make it a little bit easier so you can see what I'm talking about. Right here, you use this table in this equation. You use this table AB and 1/3, so on and so forth. For laminar flow, A is equal to 3/4 and B is equal to 1/3. UST is the the standard for uniform surface temperature. That's what that stands for. And then USF is for uniform flux. So we were told in the problem that we have a uniform surface temperature of 80 degrees C. So we know we have to use UST for A right here, and then B is this right there. So that's how I got that equation from this table under a uniform surface temperature. I'll my paper around there a little bit. Alright, back to my notes here. So then, if you solve out this equation, you'll end up with HL, because we're still looking for HL, just like the last problem. We have the same Q flux and Qmax over here. This is going to be equal to K over L times 0.453 Reynolds to the 1/2, Prandtl to the 1/3, all over 1 minus zeta over L to the 3/4 to the 1/3. Okay. Now putting the values in here for this. K and L. L is the new 0.03 from this total length. L is always the total length of the entire system, no matter what. And then all the other values are basically the same from the previous part of the problem. So we've got 0.0282 watts per meter Kelvin all over 0.03 meters times 0.453. I'd like to talk about this 0.53. This kind of varies from equation to equation. It's not an absolute constant. And it's weird because the Nullset numbers, they vary like that. And I really don't have an explanation for it. Except that, well, that's the way it is. So talk to your professor about the Nullset equation that you want to use. Sometimes this coefficient is like 0.65. Sometimes it's a 0.45. And I've never really had an explanation of how you decide what this value of the Nullset number equation is. So just be wary of that and compare it to your own notes in your class to figure out what you're using for this equation. And then this is 32,951, which is the Reynolds number for the second system, 1/2. That's 0.703, which you'll look up in table A4 if you're using the Incapura heat and mass transfer book. Then this is all over 1 minus 0.02. Zeta is the starting length. So the unheated starting length is zeta right here. So that's where the 0.02 came from. All divided by 0.03, which is the total length, L, to the 3/4, all to the power of 1/3. If you solve that out, this is all equal to HL. HL is equal to 107 watts per meter squared Kelvin. And if you solve for Q double dot of L, equal to HL times Ts minus T infinity, 107 times 80 minus 24, you'll end up with 6,013 watts per meter squared. So then Qmax with an unheated starting length is equal to 0.001. Oh, sorry. Yeah, okay. Double check that. Make sure I didn't do anything wrong there. Meters squared, which is the area of the surface, basically. Times. Oh, wait a second. That's odd. Let me check anything real quick. This Qmax is equal to AS times Q double prime. Area of the surface is 0.01 times 0.01. Yeah, I think that's right. So you'll notice that in this solution, the area is just of the chip, and we're not counting the unheated starting length. Because really, when we're looking at Qmax, we're only looking at the heat flux, which is why we're using this equation up here, which is the heat flux over a particular area, and this surface only includes the heated chip. So this Qmax, the area is only of the heated area. So AS, you could say heated area when you're looking at it, just as a way to define that for yourself. The AS is only of the thing that's given off any heat. The unheated starting length is not relevant to figuring out how much heat is given off because it's not giving off any heat. So this is times 6,013 watts per meter squared, which is equal to 0.6 watts. And that, if you'll compare this to the one without the unheated starting length, you'll notice that you actually, actually have to use it takes less power to heat up the chip in this case with the unheated starting length. So there's really no reason to have that substrate there because it decreases the amount of power that chip is able to withstand without overheating. Whereas over here, you've got 0.06 more watts that you can pump into that chip, so that gives you a little more leeway in design if you're thinking about it that way. So there's really no useful engineering resource for this unless you're trying to restrict the range that your chip can have without failure, which I don't know why you would do that. But that's how you figure out the Q, or the heat transfer rate of a certain object within a given, with an unheated starting length, with and without an unheated starting length.